Hello everyone. Today I'm going to give you a presentation about subdivision wavelet on 3D mesh. As an overview, first I will review the traditional wavelet transform and then introduce the multi-resolution analysis, which is a design method for the wavelet transform. Then talk about the implementation about the wavelet transform for 3D mesh. And in the end, I will talk about some pre-process for the wavelet transform. First, let's recap the traditional wavelet transform in my last presentation. This figure is a wavelet transform implementation by the filter bank algorithm. The output of each filter composes the wavelet coefficients. See a real example. On the left is a 1D signal. And after we do a wavelet transform, we got a result. The wavelet coefficient looks like this. And this part is the approximation part, and those are the details of the input signal. And for a two-dimensional signal, we just apply the one-dimensional wavelet transform along xy directions respectively. Get the wavelet coefficient. We still have approximation and some details, horizontal details, vertical details, and diagonal details. So if the input is 3D mesh, can we apply the wavelet transform along xy directions? The answer is no, because the data in the mesh is not uniformly sampled. Means the vertices in mesh is not sampled uniformly on the XYZ grid. So if the three-dimensional input is represented by a very dense point cloud, which is sampled uniformly on the XYZ grid, then we can do the traditional wavelet transform. But mesh is not in that case. So mesh is really represented by some non-uniform vertices and the topology. So we need some other wavelet transform. And in this presentation, I will show you another wavelet transform that can be applied to 3D mesh, and it also has a similar structure like the traditional wavelet transform. Okay. Before that, I'd like to introduce a multi-resolution analysis, which is a design method for the wavelet transform. Also the justification for a wavelet transform. So that means if we want to design some wavelet transform scheme, we need to find some key ingredients. And the first key is nested spaces. So a space is just a site consists of data with a certain resolution. So the subscript is a certain resolution, and a larger subscript means a higher resolution. So the nested space means the lower resolution is a subset. The data in a lower resolution also exists in a higher resolution space. So you can see V0 is a subset of V1 and a subset of V2, a subset of L2. So L2 space just means the spaces have finite energy, finite information. So given the subset relationship, we can, for a higher resolution space, for example, the V1 can be decomposed to V0 and a lower resolution space V0 and its complementary part W0. So V0, the intersection between V0 and W0 is an ampersand. Means the data, the information in V0 that exists in W0. And the orthogonal sum of V0 and W0 forms the space V1. Okay. More generally, space Vn can be decomposed to Vn-1 and Wn-1. We can further decompose the space Vn-1. So here the space Vn-1 is called the approximation space. So it just approximate space Vn with light data. And the space Wn-1 is called the wavelet space, has a details in V space Vn, but not in Vn minus 1. Okay, don't be scared by that. I will show you an example. So suppose a two-dimensional figure is in a space V1, and after a Wavelet transform, the space V1 is decomposed to V0 and W0. So the V0 is an approximation. You can still recognize the flower, similar as the input, and some details exist in space W0. So the next case, we have to find a set of scaling functions which span the approximation space. It means for every function in a space Vi, we can represent the function by a linear combination of the scaling functions. And scaling function should be shifted invariant. That means we shift the scaling function have the same shape. And the scaling function should be refinable. That means scaling function of a lower resolution space can be represented by a linear combination of the scaling functions in a higher resolution space. And the last case is we have to find a set of wavelet functions that span the basis of the wavelet space. And the wavelet functions should be refinable and shifted invariant like the scaling functions. And in addition, the wavelet functions should be orthogonal to the scaling functions. So until we find these three key ingredients, we can perform a wavelet analysis. So for a function in a higher resolution space, Vi, and the space can be decomposed to V0 and W0. We found a set of scaling functions and wavelet functions. The input function can be represented by a linear combination of the scaling function plus the wavelet functions. Okay. It's a mathematical form of wavelet analysis in my understanding. Okay. So let's say the traditional wavelet transform. So the low-pass filter followed by a two downsamplers just project the input function to the approximation space. That's the approximation coefficient, and the high-pass filter followed by a two four downsampler just project the function to the wavelet space. We call the wavelet coefficient. So the filtering operation of the convolution is just a sum of the inner product of the input function and the shifted scaling functions. So the input is a sequence of size 2k, and the wavelet transform. The result of the wavelet transform is approximation part and the wavelet coefficient. So as a traditional wavelet transform won't work on 3D mesh, so we want to design a new method for the 3D mesh. It means we have to find the nested space and scaling functions and the wavelet functions. And we found that if a mesh is a subdivided mesh, it means if the mesh is subdivided from some coarse mesh, for example, the mesh M1 is subdivided from mesh M0, then it's easier to find those three properties. So, for example, the nested space, you can see obviously the vertices in mesh M0 also exist in mesh M1. If we subdivide mesh M1, we can get some even finer mesh, and the vertices in M0 also exist in finer meshes. Okay. We also need to find a set of scaling functions. So usually the scaling functions defined as a height function. So the shape looks like this. So given a vertex, the scaling function has a value at this vertex is 1, and decays to 0 to its direct neighbors. And also this set of function, this height function, set of the height function can form the basis of the space of the mesh. So for example, if the function is the surface itself, for any points on the surface, we can represent it by the set of scaling function plus the multiplied by the vertices on the mesh. And the scaling function is refinable since it requires a long proof, so I would skip it here. Just keep in mind it's refinable. Okay, until now the low-pass filter is constructed similar to the traditional case. So the scaling function plays a role as the low-pass filter. So we need to construct the high-pass filter similar to the traditional case to do the Wavelet transform. Okay, so Wim Surveillance has proposed a method to construct the Wavelet functions, the high-pass filter. So it's called lifted Wavelet transform. Here the high-pass filter is just a computation mask that iterates over all the finer vertices. The finer vertices is like, for example, if the input mesh is subdivided from coarse mesh M0, and the finer vertices, just the vertices that exist in the input mesh but not in the coarse mesh. The finer vertices are the newly added vertices by subdivision. And the coarse vertices are the vertices that exist in the coarse mesh M0 and also exist in the input mesh M, the finer mesh M. So the D operator just separates the coarse vertices and finer vertices and let the coarse vertices pass the low-pass filter and let the finer vertices pass the high-pass filter. And the low-pass filter in the lifted Wavelet transform is just a delta function. It does nothing because the convolution with a delta function is just a function itself. So in the coarse vertices past the low-pass filter, we got a mesh, M-coarse mesh. It can approximate the input mesh, but cannot achieve the best approximation because remember in the subdivision scheme, the coarse vertices, their geometry is also affected by the finer vertices. So we have to remove the effect from the finer vertices. We need to add a scaling factor and can cancel the effect from the finer vertices. So the S is just a lifting factor to update the values at coarse vertices to achieve the best approximation. So that's why it's called lifted Wavelet transform. And on the left part is a forward Wavelet transform, and the right part is a backward Wavelet transform. So in a general view, the lifted Wavelet transform takes either input function depend on a subdivided mesh. So the subdivided mesh means mesh has subdivision connectivity. So why the subdivision connectivity is important? Because it guarantees the nested space and scaling function refinement properties. So in my understanding, it is similar to the downsampler in the traditional Wavelet transform. So we know which vertices we can remove and which vertices we have to keep. So the other input is the topology site, connectivity site for the finer mesh and the coarse mesh. So we can separate the coarse vertices and finer vertices. the output of the forward Wavelet transform is a scalar value associated with each vertices in the input mesh M. Or not a scalar value, just the same dimension as the input. Also approximation and some details. Okay, until now, since the low-pass filter and the operator D, the implementation is trivial. So what we need to do is just implement the high-pass filter and the scaling factor. Okay. Let's say the implementation. So given a function depend on a mesh is subdivided from some coarse mesh. So we know which vertices is coarse vertices and which vertices are finer vertices. So here's an example on the website. So the white vertices are the finer vertices, and the black vertices are the coarse vertices. So the first thing is calculate the lifting factor. So first we have to initialize the scaling factors on every finer vertices as 1 and coarse vertices as 0. And for a given vertex k, vertex k is this vertex, and we retrieve its A-type neighbors, A-type coarse neighbors, B-type coarse neighbors, and C-type coarse neighbors. And then for every A-type coarse neighbors, we update its scaling factor by this equation. And for B-type coarse neighbors, update its scaling factor by this equation. And for C-type, for every C-type neighbors, update their scaling factor by this equation. And next is to calculate the Wavelet coefficient for every finer vertices. So it's calculated by this equation. It's a function value at vertex k minus the sum of the function value at A-type vertices divided by 2, and minus the sum of function value at B-type vertices divided by 8, and the sum of the function value at C-type vertices divided by 16. And then we have to update the coarse A-type coarse vertices function value by this equation, because the scaling factor is calculated before, and directly update the function value at A-type coarse vertices, and then move to the next finer vertices. So that means in the whole process, every coarse vertices, their function value is updated. And then for all the coarse vertices, the Wavelet coefficient is just the updated function value. Okay, that's a forward Wavelet transform. And for the backward Wavelet transform, the first thing is calculate the lifting factor. But before we calculate the inverse Wavelet transform, we have to update the Wavelet values at A-type coarse vertices. So first we do the update. We do the updating. Update the Wavelet values, and then for every finer vertices, the sign change. Okay. Next is calculate the inverse Wavelet transform value by this equation, similar to the forward Wavelet transform. But the sign is changed. And the last step is the same. So just assign the update Wavelet transform or Wavelet value as a inverse Wavelet transform value for the coarse vertices. That's a implementation about the lifted Wavelet transform. So let's say the relationship between a subdivision and a Wavelet transform. So the top figure shows a Wavelet transform process of a subdivision process, and the bottom figure shows a Wavelet transform of an input mesh. So obviously, the Wavelet transform can be seen as an inverse process of a subdivision. So subdivision just keep adding vertices to a coarse mesh and get a finer mesh, a smooth mesh. And the Wavelet transform just remove the vertices from a coarse from a finer mesh and get a coarse approximation plus some details. So remember, for the lifted Wavelet transform, we require a subdivision connectivity, and we also need a topology size that define connectivity for the coarse vertices and the finer vertices. But it's awkward to ask a user to provide that, so we need some algorithm to calculate the coarse topology. So here are two algorithms. So the first is a coarsen algorithm that can calculate the coarse topology. It can calculate which vertices belong to the coarse vertices set and which vertices belong to the finer vertices set. The first algorithm is coarsen algorithm. It's proposed by Kai Holman. It's derived from the vertex property in subdivision. So in the subdivision, the interior regular vertices always has a valence of 6, and boundary regular vertices always have a valence of 4. So for triangular subdivision, it only generates the regular vertices. So you can see the irregular vertices always exist in the coarse mesh. So the irregular vertices in a finer mesh always exist in a coarse mesh. It should be a coarse vertices. So since the algorithm is not a trivial implementation, so let's just show you the input and output. So the input mesh is a finer mesh, and after we repeat the coarsen algorithm, we can get the coarse topology of the input mesh. But this algorithm has this limitation that if the input mesh doesn't have irregular vertices, then it won't work, because the algorithm don't know where to start the algorithm. And the second algorithm is covering mesh, proposed by Gabriel Tobin. Utilize the face properties in subdivision. So a coarse face is subdivided into 4 finer faces for a triangular subdivision. So this algorithm is also not a trivial one. So we just show you the input and output can do the same thing as the coarsen algorithm. Given an input finer mesh, we can separate the coarse vertices and finer vertices as the input to the Wavelet transform. Okay. The conclusion. So the lifted Wavelet transform works for the mesh of arbitrary topology, but it requires the mesh have subdivision connectivity. And it can be used for the mesh compression or mesh watermarking. Also, it has a similar structure to the traditional Wavelet transform. It has a similar result. Given an input finer mesh, we can get a coarse approximation and some details. Here's an example. Suppose the input is a mesh geometry, and after the Wavelet transform, we can get an approximation, and those are the details. It's very small. The values are very small, so I render as the norm of the Wavelet coefficient on the finer vertices. So you can see a lot of holes on the mesh because the coarse vertices are removed. And the darker value means a lower Wavelet coefficient, and the lighter value means a larger Wavelet coefficient value. So we can see at some smooth area, the wavelet coefficient is very small. At some detail part, the wavelet coefficient is slightly larger. Okay. Do you have any questions?
Well, I have a question in terms of the implementation. I was wondering, is there any library out there to kind of handle those sort of operations, or you are supposed to kind of write the whole thing from scratch in terms of the implementation, software implementation?
I think I'd like to use for the data structure, I would like to use Seagull. And for the calculation, I think it's not too difficult. I would like to implement from scratch.
Okay. But I think there are some libraries, there are some functions in Seagull that you can use for the subdivision. Yeah. But I think in terms of the wavelet,
it's just need a subdivision connectivity, then need subdivision.
Yeah. I mean, in terms of the wavelet implementation, it's not implemented in Seagull, right? Wavelet.
Yes. No.
Mesh
no,
wavelet.
Not in.
Okay.
So let's assume that I give you a random mesh model. So how can you tell me whether it has a subdivision connectivity or?
The two algorithms can do that.
Okay, so it
can verify if you have a subdivision connectivity.
Okay, so if it doesn't have a subdivision connectivity, how can you do some pre-processing?
That may require the remesh process, but it's beyond my scope.
Okay.
Remesh your random mesh to a mesh has subdivision connectivity.
Oh, yes.
I'm wondering what's the mesh format you use? Is that still object?
It doesn't matter. I mean, in my final program, I think should accept any mesh format, like say object or STL.
And any format.
As long as it has a triangle mesh, I think it's okay.
Because normally in our group we use object file format. I think maybe you still use some.
Yeah, I think it just depends on the interface. Like how you convert the file format to the Seagull data structure or something. The half-H data structure.
When you go to implement things, you have to decide what format it's in, right? Because it can't just magically materialize a data structure in Seagull. It has to read the data in some format and parse it. So probably I would guess you would probably use whatever Seagull supports. So you were talking, I think you were alluding to the polyhedron 3 class in Seagull is probably what you'd use to represent the mesh. Because in response to like Ali's question, as Stephen was saying, the most difficult thing is representing the mesh. Everything else is kind of relatively speaking, kind of easy compared to the class that represents the mesh. So use Seagull to represent the mesh, and then you layer on top of that your own code to do things. But Seagull also provides support to do I/O. It can handle OFF format, because I know some people use that. I think it might also handle some other formats, but I honestly don't know. So I guess probably what you would do in your project is you would use whatever Seagull supports.
Yeah.
Just say, I'm using Seagull to like basically read these things in. Whatever it supports, that's the format you have to use. Otherwise, you're forced to have to do additional parsing and stuff in it. It might be kind of messy to do your solve sort from scratch. Ask. You don't have to, but if you have any question, there's no such thing as a stupid question. Just okay.
Let's go back to slides 11. I'm actually less clear about the difference between the type A and type B version.
So, for example, the vertex K is here. So the K is the direct neighbor. The A is the direct neighbor.
Oh, okay.
Yeah.
Just connect to
connect to the finite vertices. A is the coercive vertices, and B is also a coercive vertices.
Please not connect to that.
Yeah, not connect to vertex K in the finite mesh.
I'm not sure if I'm understanding this figure correctly, but if I am, I think the way you're presenting it may be confusing to people who have background in subdivision, because like for the most people here, except them, everyone has taken like the 586, so they know subdivision, or at least they knew it at some point in time. And basically, this is just like the templates, right? You have a template which gets overlaid onto the mesh, and it tells you how to weight the different vertices. But he's presenting it in a totally different way. But effectively, at least if I understand correctly, I think that that's all this really is. Except it's like a polyphase representation of subdivision. Like when we implemented it, you just had like a template. You apply it, you weight things, and add it together. You're done. But instead, you can split that into operations where you partition the vertices of the mesh into the old vertices and new, so you have two sets. And then what you can do is you can take weighted versions of these things, add them to these things, then weighted versions of these things, add to these, and you go back and forth through different weightings. This is called a lifting implementation. It's like a lifting implementation of a filter bank. I don't know if we talked about it, but it's in 586, but it's just a polyphase representation that uses a ladder network. So you split into polyphase components, you have two channels, the two polyphase components, and then you add a filtered version of one channel to the other, and then filtered version of the bottom channel to the top, and you keep alternating between them until you're done. It's a similar kind of thing here, I think. But it's presented in a very different way. This is not to say that this is the wrong way to present it, but just if people have a certain background, if you present it a way that's kind of very different from the background they have, it would be much more difficult to understand. So it's not necessarily the case anything's wrong with what you're presenting here, but it makes it a bit more difficult for people with a subdivision background to understand. Maybe one other comment I should make, which you didn't mention, is that you're assuming a particular wavelet transform here, because from people who have wavelets before in 586, there's no such thing as the wavelet transform. There are an infinite number of wavelet transforms, which correspond to just different choices of filters in a filter bank. Similarly here, there's different choices which would correspond to different subdivision algorithms effectively. Like there's different ways you can subdivide, different weights. Each different choice of weights will correspond to a different transform. And these 1/2s and 1/8s and 1/16s you have here are implicitly assuming, I'm not sure which one it is, it looks like it might be butterfly subdivision, but I'm not sure. Looks like you're implicitly assuming one of them. Probably in your project, you'd want to allow the user to specify like what the coefficients are, and then you just apply them. You assume that they give some correct coefficients and then apply them. Yeah. But for presentation purposes, it's okay to maybe assume one, but you should probably point out that which particular one you're assuming, and just so that people are aware that there are more than one wavelet transform. Any other questions? I had a few comments here. The first one is, actually I don't know what happened at the beginning. I could have sworn that there weren't numbers on some of the slides, but now there are numbers on the slides. So I don't know if it was just some of the slides don't have numbers, or okay, some of the slides don't have numbers, I guess. I thought maybe I was hallucinating after a while. I could have sworn that some slides didn't have numbers, and then suddenly they all have numbers. Well, anyway, make sure that all the slides have numbers like this. If it's just maybe you're doing the slides stepwise or something, and maybe earlier ones don't have numbers, I think you can fix that so that they all have numbers. Just because it gets confusing for kind of people who are trying to refer to a slide number to ask a question. If you have only some of the slides numbered, then what will happen is someone will have a question about a slide that doesn't have a number, and then they don't have a way to reference it. Please spell check slides. If you're using LaTeX, which I assume probably are because this looks like Beamer, you can spell check because there's tools that actually even know about LaTeX format, so they spell check and they won't say every LaTeX macro is a typo. I use ASpell, but there's probably other tools as well you can use. But please do that because I noticed quite a few typos, and it's not a big deal for a presentation for our group. But if this was a presentation that really mattered, like your MEng exam or seminar or something, it's kind of embarrassing to have typos because it just shows that you weren't that careful, and it could create a negative impression, especially like in an MEng oral exam. You definitely want to make sure you spell check for that. But get into the habit of it, because if you don't do it consistently, then when it really matters, you'll forget. Slide number 9, I had a question about, or I was wondering about. Like, I think maybe we can take this discussion offline to a certain extent, but I'm not sure that what you're saying the inputs and outputs are necessarily what I would say the inputs and outputs of the lifted wavelet transform are like the inputs to the wavelet transform. I would say like the forward wavelet transform would be you give it some refined mesh, like some detailed mesh, and then it will output a coarse mesh plus sets of wavelet coefficients. And then the output is kind of the opposite of that. You give it a coarse mesh and some wavelet coefficients, and then it will output the fine mesh, something like that. But this, at least if I understood what you were talking about when you were presenting this slide, it seems like you're presenting something a bit different. So maybe we need to talk about that. But at least unless I'm having a misunderstanding, because you've been doing a lot more reading about this than me, but I think that my basic understanding is correct. If that's the case, then I think that this might be a little bit misleading, but I'm not 100% sure, so we need to maybe take this offline. But just in case my suspicion is correct, I just want to, for the benefit of the people who are listening, point out that maybe more traditionally the way you would present the input and output would be the way that I just described. See on slide, oh, okay, we talked about that slide 10. Slide 16, just when you were plotting the wavelet coefficients, I just want to point out that because people here that are new to this might not realize this, like the way, I think the way you've plotted the wavelet coefficients don't really make sense, because the wavelet coefficients are fundamentally different things from the coarse mesh. Like the coarse mesh that you get when you do the wavelet stuff, like the forward wavelet transform, you get a coarse mesh plus wavelet coefficients. The coarse mesh is basically like a manifold or something, like it's a surface embedded into 3D. The wavelet coefficients are a totally mathematically different thing. They're just vectors in 3 space. So that like, they have an x, y, z component. They're just basically scalars, like number. Well, not scalars, but vectors of scalars. So I don't know if it really makes sense to plot them this way, because when you plot them this way, to people who maybe don't know it, it just kind of makes it seem like the wavelet coefficients are the same sort of thing as the mesh. But they're not. They're very, very different kind of things. So this would be something I would emphasize.
Real wavelet coefficients, very small. I just want to make it clear.
Yeah, but I understand what you're presenting. So I mean, the idea that you wanted to convey that the wavelet coefficients typically are small for a lot of types of data sets, this is maybe a good idea to convey, because this is one of the reasons why wavelet transforms can often be quite useful, like in practice, why they kind of work well for a lot of applications. But it's still nevertheless kind of misleading to show this picture, because again, these people don't know this stuff yet. You're trying to teach it to them, right? So when you put the things all on the same figure, it kind of makes it seem like they're the same thing. So I don't know. You could maybe ask some of these people. I mean, I'm only guessing, but my guess would be some people might think that everything is the same type of thing mathematically. Like the wavelet coefficients are kind of the same sort of thing as the coarse mesh. Because like in the traditional wavelet picture, they are kind of the same thing. Like you basically just have numbers. You have your output of one subband channel of a filter bank. It's a bunch of numbers. That's the coarse data, and then you have the values of coming out of a high pass filter, whatever the high pass channel. Just a bunch of numbers of the wavelet coefficients. Like in the traditional case, everything's basically just the same. They're all just numbers. But in this picture here, like you're getting fundamentally different things. The wavelet things are very, very different from the coarse thing. One is a mesh, like a manifold, effectively. The other is just vectors in 3 space. But there's nothing wrong with trying to convey the wavelet coefficients are small. I mean, they don't have to be, but you're right. Like, usually for data sets that are not like wildly oscillating, they will tend to be relatively small, and that has benefits in compression and so on. Yeah, that was all the comments I had. Anything else? Okay, well, thank you for your presentation then.
Thank you.